Hello, my name is Michael Lawrence Garcia. I represent the Columbia University Robotics Club, a student organization at Columbia University dedicated to developing and advancing the bleeding edge of robotics. We are advised by Dr. Hod Lipson of the Creative Machines Lab at Columbia University. In the winter of 2021, the group of 15 students pictured on screen developed a proposal for a novel snake-like robot, Diana LT, which is able to traverse steep slopes on the lunar surface. Over the course of several months, two subteams researched, designed, and analyzed a robotic mobility platform that can deliver small payloads in support of Artemis operations. Potential applications include the traversal of spotlight craters and lunar lava tubes. I am very proud to hand it over to the subteam leads to discuss their work on the project.
The proposed solution is to be constructed with carbon fiber tubes, universal joints, linear actuators, and microspine grippers. Microspine grippers will be attached beneath each joint, allowing the robot to grip rough, porous, and dusty surfaces. To provide the robot with the information needed to navigate the insides of lava tubes and crater slopes, Diana LT uses a stereo camera above the frontal joint paired with two LiDAR sensors located at the front and rear end, thus providing each joint with the necessary information to correctly find a place to grip. Linear actuators at each joint will provide pitch and yaw control, which in tandem with the grippers will make the robot move. The robot will use a horizontal slithering motion when possible in order to keep a low center of gravity. However, in narrow channels, the robot can use a vertical looping gait, like an inchworm. Payloads can be carried in containers at each of the joints or externally secured to the linkages.
To simulate the gait of the rover, we created a skeleton and isolated the parameters of the linear actuators needed for movement. Then, we applied an evolutionary algorithm and determined the best gait against a fitness function optimized for the maximum distance covered from origin. All of this was done on a self-programmed physics simulator, which gave us maximum control not only over the geographical features in the landscape, but also over natural forces like the gravitational force on the moon. In another iteration of the simulation, we incorporated different materials in the skeleton to account for the various materials used in the rover and observed its effect on the gait. In a test simulation, we removed some parts of the skeleton to simulate damage in the rover and attempted to let the rover intelligently work around the damage to change its gait accordingly. In the upcoming phases, we plan to simulate the model in PyBullet by converting the CAD model to URDFs and making the simulation of the resilience of the robot to damage more robust.
Thank you for watching our proposal for Diana LT. We are confident that this design can bring NASA and the aerospace community a new host of possible system architectures. We hope that you see as much potential in Diana LT as we did.